J'espère que tout le monde est là. Encore des gens. Quelqu'un sait s'il manque une personne au moins? Votre collègue? Second thing is, do you want me to speak in English or in French? So this is my level of English. You want. So who wants English? At least one person, right? So I will speak in English. Yes. Alors c'est sur ma page web, du coup, je sais pas, vous avez dû recevoir un mail, non? Avec les informations? Non? Je vais vous donner l'adresse. Elle doit être ici. Quelque part. Non, pas là. Ok. Ah, on va le voir. Donc, vous avez normalement dû recevoir un mail avec l'information de ma page web que vous voyez là-bas, cazaberemy.fr, cazabetremy.fr. Et sur ce site, vous avez toutes les informations, y compris donc ici. Donc là, vous allez dans Teaching et Complex Networks, si vous n'avez pas le lien direct. Et là, vous avez normalement e-learning setting et vous avez l'adresse à laquelle vous pouvez vous connecter. Alors, si possible, ne vous connectez pas pendant le cours, parce que sinon, le Wi-Fi risque de pas tenir le choc et ceux qui sont à distance, ils vont plus rien entendre. Ok. Et je vous mets aussi, donc j'enregistre normalement le cours. Donc, normalement, si tout fonctionne correctement, vous pourrez accéder à l'enregistrement. Maintenant, je connais pas encore la qualité, donc on verra au prochain cours. C'est un peu une expérimentation. Et sachez aussi que tous mes matériels, je vais peut-être déconnecter ça. C'est d'autres cours. Donc vous avez aussi un Discord si vous voulez pour échanger, mais peut-être pas pendant le cours. Et donc tout le matériel que j'utilise est disponible. C'est-à-dire que je partage des petits documents comme ça où vous avez un résumé de toutes les définitions, etc. Et les slides, évidemment, sont disponibles aussi. Donc, a priori, tout est disponible. Et donc, ok, je vais aussi expliquer ça dans mon introduction. Donc, je vais détailler un petit peu plus. D'autres questions sur le démarrage? Okay, so let's go back. Switch back to English. So first, who am I? So my name is Rémi Casabé, and I'm associate professor at the Université Lyon 1. I'm a member of the LIRIS lab, so data mining and machine learning team, and I was trained a computer scientist, but now I'm considering myself a network scientist because it's my main field of research, and we will see that it's a real thing. Network scientist, it exists. And I'm also a member of ICSI. I think that you all know ICSI now. Most of you professors are part of ICSI, the Institute of Complex Systems in Lyon. I already gave you the website. You have the link here. You have my email. Don't hesitate to send me emails if you have questions. And I sent already also an email that you should have had, but if you don't have, so please send me an email right now if you have not done it already with just information which is your name and the master you're part of, because there are students from several masters following this class, from physics, computer science, biology, cognitive science, and so on. So please send me an email with this information, and this way I can send email to you on this mailing list, and don't forget anyone. So if you know that someone is not here today, also give the information that he or she send me an email so that I can contact this person. Okay, you have the address. Good. I also gave the information about the e-learning. It's recorded, and you have the address here. And there is also a Discord channel for those who want. So if you have a question which can be useful to everyone, like about exams, about something else, you can post it in the Discord channel so that everyone can see it and see the answers. But it's, no, okay, you don't have to use it. A short overview of the class. We have 24 hours of lectures together and 3 tutorials of 2 hours with someone else, Lorenza Bazzini. She will teach these tutorials. And for the exams, we have two grades. There is for lectures, which is a rated exam. I think it's 2 hours in January. And so it's mainly questions about a scientific article. I will give you an article and you have to comment it. So you don't have to learn by heart any definition. You can use all the documents I provide, and it's more to see if you have understood and if you're now able to read a scientific article in the network science field and to understand most of it. And finally, the other grade is a project. So you will have to code something in Python or using another software, GEFI, and you will analyze a network, basically. So you have to understand something interesting by analyzing a network with the tools we have seen during the class. So this class today, because I knew that several of you had no way to get the information before, so I had to warn you before. So this class is the only one in which I will talk for 2 hours because it's difficult for me and boring for you. So I will, usually in all the other classes, I will split in 2. The first hour, I will explain things, and the second hour, you will experiment some things. You will practice what I have explained on some real networks. So this means that you need to have your own computer. So today you don't need it, but since from Thursday, please bring your computer. If you cannot, try to work in 2. So I know there is the COVID situation, but if you're careful enough with people who already eat together, for instance, you can share a computer. And I will try to bring some plugs, but it will be difficult. So please try to charge your computer before coming. So yeah, you have to install also those things, basically Python and GEFI. So for the first class, we will mostly use GEFI, so try to install it. And just after, so next week, you will have the first practicals with Lorenza, and she will help you if you need to install more software or if you don't know at all Python. She can help you for the beginning, and so on and so forth. So as I told you, I provide some all the documents, so you don't have to take notes while I'm talking. And okay, that's all for the introduction about the class. So do you have questions about what I've said already, or the class in general? No. Okay, fine. Yeah.
Also, for lecture will be like will be alone.
Yeah, you will be by groups of. Yeah. Another question? No. Okay. So let's start the class for good. Again, it's a general introduction to explain why we should study complex networks. Okay, it looks fun, there are graphs and everything, but in the end, why is it interesting now to study this in particular? Or is it just because we are all a fan of complex systems, so we want to study it because it's part of complex system? So I will start with a very, very general introduction by asking what is science. So for me, so it's a very naive definition, of course, but science is about understanding how things work, okay? So the general idea is I want to understand how, I don't know, the human body works, or I want to understand how, I don't know, that objects fall to the ground works, and so on and so forth. So I would like to understand things. And historically, what people were doing in the beginning of the scientific method is to experiment with the objects that we want to understand at the macro level. So, for instance, if I want to understand how object falls, I will take objects like a stone, and I will, I don't know, throw it, or I will let it fall from a given height, and so on and so forth. And I experiment with this object for trying to understand this object. And it was quite successful. You all know the stories of discovery of gravity and so on and so forth. And that's the first way. If I want to analyze the world, I take the objects and I analyze this object. Then there was kind of a revolution. The great success of the 19th and 20th centuries are an approach called reductionism. So reductionism is the idea that if I want to understand an object more than just manipulating it, I have to understand what it's made of. Okay, so I will take what I'm studying and check inside. So for instance, if it's the human body, I will check inside and I will see that I have organs, I have maybe vessels. Inside these organs, I discovered that I have cells, and this helped me to understand how the human works, how the body works, because I understand the parts. And then I go deeper and I discover DNA, proteins, and a lot of other things, nucleotides, and so on. If I'm studying objects where I see that these objects are not made of a single thing, they are a little bit more complex than that. There are organic compounds, there are atoms, there are protons, electrons, neutrons, and a lot of other stuff that probably the physicists here know better than me. And this was very, very successful. It made a lot of discoveries about how the world works, and it was amazing. But the problem is that now we kind of reach the limits of this approach. Because basically we know everything about what things are made of. If I take the human body, basically we can understand, we know every pieces of this human body. We know all the, basically all the atoms that are inside. And if I want to take a better example, I can take the brain. So if you take the brain, we know exactly, the human brain, we know exactly how many cells there are inside. We know how many connections. We know what these cells are made of. We know how they kind of interact. So we know basically everything about how the brain, what is inside the brain, but still we don't understand anything about how from this brain there is something which is emerging, which is the mind and intelligence and so on. We understand some things, but not the whole thing. And this is because this system is not homogeneous. It's actually heterogeneous, and it has a complex structure. So what is very important to understand what's going on inside the brain, it's the interactions and how these interactions are organized. And so it's the same for society. For instance, if you understand the people, you don't understand the society. You need to understand how these people interact. And so the structure, the relation, the interactions matters, and networks are designed to represent these interactions. That represent the structure of a system. So of course, complex system, you already had the introduction, but they are systems composed of multiple parts in interactions. You have this word, interaction, so it means that if you want to understand a complex system, you have to understand how the parts interact. And if you want to understand this, you need to model it using a network. Yeah, so complex networks are a common framework applicable to many systems, so you can use the same tools to study different things. And here are examples of things that you can study, so basic example, but you have here some Facebook network of friendship. Here you have some network of the public transportation in Lyon. Here you have a food web. So here who is which animal is eating which other animal. Here you have some examples of economic networks, so exchanging goods between companies or people. You have here some materials, right? So you can model what materials are made of. If you think about it, the difference between carbon, basic carbon, and a diamond is mostly the organization, so how things are organized inside. If you look here at the pattern of streets in different cities, you see that you can recognize where this city is located, maybe in the world, or what is its history, by looking at these patterns, which are graphs, and the brain, the example I already gave. And this year I added a new one that you probably have seen similar things in papers recently. If you want to understand how the COVID, how a virus is diffusing in society, well, you need to study the network of people, because it's so of course there are some effects, which is wearing a mask or not, which affect the probability to share between people. But then what explains that, for instance, one country is getting the virus first and it's not spreading to another one, and then it's spreading sometimes later, and then it spreads to the whole country, or maybe yeah, this kind of phenomena are typically network phenomena. You also heard, I think, of super spreaders, things like that. They are actually network notions. So networks are everywhere, not only because I am working with networks, but also I think there is some kind of truth. As soon as you have many elements and interactions, networks are very useful. And to conclude this part, just a note about who are network scientists. So there is many people study networks, and there are several types of people working with networks. There are people that I will really call network scientists, who are often physicists, computer scientists, mathematicians, or sociologists that have introduced many notions about networks, so how to recognize some families of network and so on. So they work really on the core of the idea of a network, independently of some field of application. And then there are many applied network scientists, which are much more common than the core network scientists, who are people who take the tools of network science and apply them to their own field, which can be anything from biology, geography, economics, and so on and so forth. So, so that's why I was saying that I'm actually now a network scientist. It's because there is really a field which is emerging between these people who at the beginning had different vocabularies, different way to approach the problem. But since they are interested in the same object, networks, they started to share, to create their own field with common grounds. And to conclude this part, so in my opinion, complex network analysis should be, will become one of the basic tools of the modern scientist in general. And to give you really what I think it's like statistics or linear algebra. So especially statistics. You want to be a scientist and you're doing anything experimental, you want to study some real data, then you need to know statistics, the basics. You need to know the basics of statistics to just see if what you observe can be explained by something random or if it's something or if it's something else. And much as statistics, network science is a tool that you need to use, it's the statistics of interacting systems. So if you have interacting systems, you need to study complex network analysis. Okay. Do you have some question about this part? So let's start with a brief history of the network science field. Well, we can trace the beginning, but it will be very short. Don't worry. The beginning could be traced to Euler and the beginning of graph theory, in which the question was: can one walk across the Severn Bridge and never cross the same bridge twice in this city? And he modeled that with a graph and got the answer that no, you cannot. Okay, good. This is the beginning of using graphs to solve some real problems. I'm taking a strong leap forward, and I'm going to sociology with Jacob Moreno in 1934, who was the first to study social networks using tools, kind of mathematical tools, but not really mathematical at that time. It was more like doing a sociomatrix. So in this sociomatrix, I will put people on the on an axis, people on the other axis, and I will ask them, for instance, do you consider that your friend with this person? Okay, if yes, I will put a little cross, and then without knowing, he reinvented the adjacency matrix, so a way to represent the graph. And a little bit later, he started to make some drawings in articles. So at that point, of course, it was made by hand. So you see that it's nearly impossible to read, but still everything is here. You already have your notes, your edges, and you have your graph. And so just to show that so you see that the field emerged in mathematics, then it got very, very popular in social sciences, in sociology in particular, social network analysis. And from around that time, around 2000, there started to be key publications who attracted a lot of attention, which were really the beginning of the field of network science, which is basically taking the tools from graph theory and applying it to real social networks and to really try to understand some systems, some facts using network tools. So you have some very famous papers here. So the small world that we will study later, which was the second most cited paper of the year in the journal Nature, which is of course very famous. You have the next year, you have a paper which was the most cited paper of the year in Science, and then you have also a very famous paper in PNAS. You have the most cited paper ever in Nature Genetics, which is called Network Biology. The most cited paper ever of the WWW conference, which is a major conference in computer science, is called What is Twitter, Social Network, or News Media? And these papers really started to create a field which is network science, and which is not, you see that you have publications by physicists, by computer scientists, and that all contribute to this field. I have some books to recommend if you want to know more. Two in particular. This one because it's available free online. So if you want to go deeper, maybe in some topic, you can check this book. And it's well done how it's proposed online. It's a website. And this one I have a copy. So if you want it, just tell me and I can bring it to you. It's very new. It was published last year. Some other books. This one are more to show that there are books on networks and something. So networks and biology, networks and economy, network and things. So if you're interested in a particular topic, you can look at what is the state of the art in using networks to study this field. More interesting, I think, if you want to read what you need, if you want to go to know more about networks, it can be fun to read those books, which are popular science books. So don't take everything in it as a scientific truth, but they are written by famous network scientists, Watts, Barabasi, and so on, that we will see cross their name very, very frequently. I have this one, so if you want, I can also bring to you if you want. And they are fun to read. I mean, it's really interesting. Finally, some examples of journals that emerged in recent years. So you have the Journal of Complex Networks, Network Science by Cambridge, Applied Network Science, just to show you that you have these journals that now, so they emerged in the last 10 years and show how the field is structuring. And you have also conferences like this, whatever. Yeah, you have the program of the lectures, which is also on my website. And now we can really start to discuss graphs and any question on what I explained about the history of network science? I also need to make short breaks because the mask. So someone told me that many classes started with the introduction of what is a graph in this master. So mine is the same. After this introduction, I will start by explaining what is a graph. So just a word, some vocabulary. So I will use networks and graphs. Actually, in network science, these words are kind of interchangeable, but if you want to if there is a difference, graph is the mathematical object, and networks is more some object in the real world. So the World Wide Web, the internet, are networks, and a set of nodes and edges is more graph. But actually, many people use them interchangeably, and so you kind of use with networks the word node and link, and with graph you have vertex and edges, but actually we can use these words interchangeably, so it's not really important. And finally, here is my introduction of graphs. So you have seen that, so for those who have not followed the other classes, you can see that a graph is defined as G with a set of vertices and edges, and you have you can define one node as U, for instance, which is part of V, and you have an edge which is noted in this way. So here is an example of a graph, and here is the example of the corresponding graph notation. Okay, easy. When we will manipulate it during the second part of each class with a computer, so we want to manipulate this graph. We won't manipulate this mathematical object, but we will use some software in which we can directly interact with terms like add edge, add nodes. So you will use this software and say add nodes, add edges, and compute path, and so on and so forth. But you have to know that behind it, actually, the way it's encoded, it's not through. So this will be an edge list, and reflects exactly what is in E. But in truth, to be efficient, the network, the graph, is usually represented in this way, which is an adjacency list. So it means that how to read it. So for node 1, the neighbors are 2. For node 2, the neighbors are 1, 3, 4. And so on and so forth. So why is it efficient? Because very often in networks, you want to know what are the neighbors of a node. Okay, so this way you can know it directly. If you have this representation, you have to go through all the edges to find all the neighbors of your node. And there are libraries, software libraries in many languages. So we will mostly use Python and NetworkX in this class, but know that there are some others which are more efficient in some settings, designed to work with specifically on some topics, of course. That's it. And now we will discuss about some types of networks. So I'm sorry, during this class, I will introduce a lot of notions. Most of them are very simple, so there is no problem to understand it. But I just need to do that in order to go beyond in the next classes. So first, an overview of networks. So the first kind of networks are undirected networks, in which edges have no direction. An example can be the internet. So in the internet, you have computers, servers, maybe that are like, I don't know, like Google, and there are connections between the two, and the information can flow in both directions. So it's undirected. It's always undirected. So most basic types of networks. Then you have directed networks in which information can flow only from in one direction and not in both, or sometimes in both. So you can define an edge from U to V and from V to U, or only in one direction. An example can be a citation network, right? If you have scientific articles, each new scientific article is citing a previous one, but this previous one is not citing your article. So it's directed by definition. Then you have weighted networks in which some edges are more important than others, like social interactions. Then you have bipartite networks in which some nodes are of different types. So for instance, you have the red and the blue, and in the definition of bipartite networks, it says that you cannot have connection between the nodes of the same type. You cannot have connection between red and red. These graphs are actually quite common. So here you have an example with gene and disease, right? So your nodes can be gene, they can be disease. We know that this gene is connected to this disease and this disease to this gene, but there is no connection gene, or disease, or you do not represent them. Yes? Yes, so in that case, it's not a bipartite, but a multipartite, but yes, you can. We will see this in a later class. Another very popular example is with in the field of recommendation with products and people. Okay, so if you represent people and what they have bought, for instance, the product they bought, or the products that they check, they browse, they check the price of, you can represent it as a graph. And then a very popular task currently is to try to predict the future edges that will appear. This is called recommendation, product recommendation, or whatever. So every time you see an ad in Amazon, for instance, or in Spotify or whatever, this recommendation is usually based on link recommendation on a bipartite network. Link prediction, sorry, on a bipartite network. So then you have multi-layer and multiplex networks. So the best is to give you this example. So you have different graphs. So the white one corresponds to street network, so the network of street in a city. The purple one corresponds to something like a bus system, for instance. And the yellow one on the top corresponds to something faster, like a subway, for instance. And you see that all these graphs are independent, but they have links between some nodes of the purple one and the white one. So it means that they are interconnected, but they are not the same. For instance, if you want to compute like a shortest path between some to go from one point to another, you know that you can compute it very easily on this graph. But if you need to change and go to this one, then you have to compute. You have to make something different, because you will have to take into account the schedules and something like that. And finally, temporal and evolving networks. We will have a full class on this, but it's also common that nodes and edges can evolve. Here you have an example. So how to read this plot. You have the time on the x-axis, and you have nodes on the y-axis. And you have connection between these nodes at particular time. So there is a connection between B and D at time 1, between C and D at time 2, and so on and so forth. Yes?
Just wait or
a 3D graph.
yes.
So what you
It's just like some way to
so you're right that quite often people will end up taking this original graph and representing it as a normal graph with, for instance, some different weights on the edges. But in fact, there are some important difference because sometimes there is something that cannot represent on this way. As I was saying, for instance, the problem of schedule, that if you start from one point here, you can cross this network. You can cross this network as you want because it's just walking. But if you want to go to the purple one, maybe it's a bus system, you have some schedule. So if you arrive at this point, for instance, at, I don't know, 1 o'clock, you cannot cross there. But if you arrive at 2, you can cross. So in this case, it's more complex than just putting some edges, some weights, and you have to make some other transformation or just model it this way. For instance, many people do things like a multi-agent system in which you will have some like little software moving around, and you can move with some rules which are very different in one part of the network or the other. Okay, temporal networks. And so let's move to introduce some more simple notions. So I will not net you the neighborhood of a node. Okay, the neighborhood is a set of neighbors. KU, so remember this term is the degree. The degree of a node is how many neighbors this node has. The successors is an undirected network. The successors are the nodes I'm pointing to. Predecessors is obvious, is the opposite. Out degree is the number of people I'm connected to, and in degree the number of people who connect to me. The weight is obvious, and the strength, so the term strength is for a node. The strength is the sum of the weights of my neighbors. Okay, so some examples. Here you have an undirected network. You see that the degree of this node is 1, this one is 3. In a directed network, the in degree can be 0. The out degree also can be 0 if I'm connecting to no one. Okay, I think it's obvious. The strength, so here you have some examples. So the red value corresponds to weights on the edges. And the blue values correspond to the strength. So for instance, this one has a connection of weight 6, another one of weight 5 and 1. So 6 plus 5 plus 1 equals 12. Okay, so this is the strength. Okay, we introduced these basic notions, yes? Yeah, you're right. If there are direction, you could also compute incoming strength and outgoing strength, but I mean, it's you can. There is not a specific name for that, but you can use it, of course, if needed. Okay, so now let's talk about describing a graph. So this was describing really the atomic properties of the graph at the level of nodes and edges. But now, if I give you a graph and I tell you, for instance, I give you 2 graphs, and one corresponds to the social interaction in this class, and the other one corresponds to the social interaction in last year's class. And I give you, can you compare them? What are the difference between them? What is similar? What is different? Then, and what can you say about it? Can you tell me if this, I don't know, the communication is going well in this class and not last year, or the contrary? So how to describe really a graph? So the first thing is to counting nodes and edges. So just counting the number of nodes, counting the number of edges, and to know if it's a lot. If I tell you are there many edges, you can compare it with the maximum number of links that you could have. And this number depends on, so it's different for directed and undirected network. But basically, if you take it for directed network, very simple to compute. It's for each node, how many other nodes there are. Well, I could connect to all the other nodes, so the maximum number is this. For the students who don't have a strong mathematical background or whatever, mathematical or physics, or if you're not used to read equations, don't worry, it's not a big problem. What is every time, so I give the equation, I give the formula, but what is important is what I'm explaining. So even if you don't really understand everything, it's not a problem as soon as you understand the general idea. So size of networks, you see that, okay, there can be some small networks, like the connection in the brain of a worm here, okay, to 280 nodes and 6,000 something edges. And you can have huge networks, like, for instance, Facebook in 2015, so it's already old. It had 1.4 billion nodes and 400 billion edges. So it's a large graph. But nowadays we can study these graphs, right? We have the techniques and the tools and the computers to study this. So if I want to compute some property on the whole Facebook, I just need Facebook to give me the data. If I accept, I can measure everything on it. Another notion is the density. So the density, so first let's look at this definition. It is defined as the number of edges that you have in the network divided by the total number of edges you could have at max. So it tells you how dense it is. But actually, it's usually easier to interpret the average degree. So average degree is just the number of the average of all the degrees of all the nodes. And if you compute it on some networks, you see that the value can be very different. But what you observe for density is that they seem for real networks to have a kind of a trivial correlation. So if I take a small network like this, I see that the density is rather big. So more than 10% of all the possible edges exist. But while I'm increasing the size of the network, this value tends to decrease. And you see that if I take a very large graph, you can get a very small value, which is obvious, right? Because on Facebook, you're connected to a very small fraction of all the possible people there are. So usually the density should not really be compared between networks of different sizes, because it's obvious that the larger the graph, the lower the density. In real networks, of course, and if you generate a network, this is not true at all, but in real network, you can observe it. Well, if I look at the average degree, well, it tells you more something about the graph, easier to interpret. So for instance, for Facebook, I can read that in average, people have 570 friends on Facebook. In average, a neuron in the brain of this worm is connected to 46 other neurons. And what is interesting is that it can be very different, like this one in the roads in California. So it's a network of roads. So you have the connection when two roads encounter at an intersection. And you see that the value can be very small here, even though the graph is big, but it's normal, because when you have an intersection, usually you don't have 100 roads crossing at this point. So it's very small. Yes?
Can you just repeat the density?
Density? So density is defined here. It corresponds to the total number of edges present in the network divided by the maximum number of edges you could have. So if everyone was connected to everyone. Okay, and it has been observed in some papers that when the graph increases in size, the average degree tend to increase while the density is decreasing, but this increase is very slow. So it's kind of logical if you think so often. It's useful to think in terms of social networks because it's something we are used to manipulate. So if you take for instance, if you take an online social network like Facebook or Twitter, it's even more obvious on Twitter. If you have more people joining Twitter, there is a higher probability that someone interesting will join. So the more people in the network, the higher the chance that you get more contacts, you're following more people. But this is not growing with the size of the network. If there are 1,000 people, I don't know, like 10 million people joining Twitter, you won't add 1% of them. Otherwise, it wouldn't be possible. Okay. So just to give some examples of analysis you can do with networks. So in this paper, for instance, in Nature Communications, they took a bunch of networks. So they took like, I don't know how many, 100 networks maybe. And for each of them, they plot the number of nodes and the mean degree. And what we observe is that there are some patterns. For instance, there are some networks that have a lot of nodes and a high degree. And then there are some other bags of dots there. So you can look at that and try to interpret it in terms of the properties of this network. Maybe some of them are social network, other ones are infrastructure network, and you can try to interpret these kind of things. So even with density, you can start to compare networks. Another important notion when dealing with networks to characterize them is to look at the degree distribution. So we will have half a class, I think, on this topic. So I won't go in details now, but basically, for those of you who are not familiar to looking at distribution, you can imagine here, if I'm talking about degrees, that you have the values of the degrees and on the x-axis, and here I'm counting how many degrees I have in the graph. So for instance, I have maybe one node with degree 1. I have 2 nodes with degree 5. I have 1 node with degree 100, and I have 50 nodes with degree 50. Okay, this is how I can read it. I have a distribution like this, bell-shaped distribution. And this is typical of what you encounter if you generate a network randomly. So randomly, for this class, it just means that I'm taking nodes, and then I'm putting edges at random. I take 2 nodes and I say they are linked. I take 2 other nodes at random and I say they are connected, and so on and so forth. So this is a random network. And if I generate a network on this way, the degree distribution will look like that. So it will be like the baseline. We could think, okay, if something is random, this is how it looks like. But in fact, if you look at a real network, most of the time they will have a degree distribution which looks like this. And this means that you have many nodes with few connections, and you have a few nodes with very large connections. So this corresponds to, so you can also again get an intuition about that if you think in terms of Twitter. For instance, in Twitter, you have a few people who are followed by many different people. So for instance, if you take Donald Trump or Barack Obama or whatever, they are followed by millions of people. But then you have the high majority of people in Twitter that, like me, they have maybe 50 people following them. And even more, you have people who just registered and never used it, and they have maybe 0 followers, right? So in many social networks, you have this, and many networks in general, you have this kind of distribution. So this is considered a property of networks. Okay, that's what I said. Another definition on graphs is to think in terms of subgraphs. So in this class, I will consider a subgraph to be defined by a set of nodes. So if I have an original graph here, I say that I want the subgraph corresponding to these four nodes, and this is the subgraph. While this is not the corresponding subgraph because we don't see very well, but so this, the pink one corresponds to the subgraph, but this purple one is not part of the subgraph, so it's not correct. So this one is a subgraph, this one is not a subgraph. We can say a subgraph induced by this node. Right, so the subgraph which is induced by this node is this and not this. So if you don't see the difference, it's this X. The color I'm not sure. But you have the definition there. Okay, it's good for a subgraph induced by a set of nodes. Yes. The two? Yeah, sorry, really, because so the idea is that you have the original graph here. I say that I want the subgraph induced by the pink node. Okay, so here are the pink nodes, and so in pink I represent the edges which correspond to this subgraph. So here they are this one, this one, this one, and this one. They are all the edges connecting the nodes. And here there is one which is missing. This one is missing. It's not while it should be, because there are these two nodes, and in the original graph they are connected. So in the subgraph, it's F should be. So I should improve my example probably. So a clique is a subgraph of density 1. It means a clique is a set of nodes which are all connected together. A triangle is a clique of size 3. Okay, 3 nodes are connected. The connected components of a graph are subgraphs with no connection to the others, but which are connected between themselves. So it's easier with an example. Here you have an example of connected components. So this is a single graph. The single graph, but some parts of it are disconnected, right? This part, all the nodes inside this part can join each other, but they cannot interact with others outside the connected components. So we will say that here we have 4 connected components. And in directed network, there is a difference between strongly and weakly. Strongly is that you have the same constraint that two nodes belong to the same connected component. Well, a connected component is a set of nodes that can all reach each other by following the path. So this is a strongly connected component. And in the weakly, it's the same thing, but you ignore the direction of path. So it's like the normal connected component ignoring direction. Okay, so clustering, the notion is the clustering coefficient. So the clustering coefficient tells you, so it's also called the triadic closure, is important because triangles are considered important in graphs. So triangles are considered to represent the fact that people are connected following some rules. And this rule is known in social network by an aphorism, which is a friend of my friend are my friends. And it has been observed that in real networks, and in particular in social networks, you have a lot of triangles. So you have, if you have A, which is connected to B, and B is connected to C, then it's likely that there is a link between A and C. And when I say likely, what I mean is that it's more likely than if it were random. So a high clustering coefficient will be an indicative of something. That is that you have some kind of phenomenon that make that if you're a friend of my friend, you become my friend. So to compute it, I need to introduce some definition. The triads of U are the number of triangles containing node U. And delta is the number of triangles in the graph. And then I have this sigma max, which is the triad potential of a node. So this means how many triangles there could be around me. And this depends on my degree, right? The more neighbors I have, the more triangles I can have around me. And the triangle potential is how many, for a graph, how many triangles there can be at max. Okay, so you can check later exactly how this is computed, but the definition of the clustering coefficient is so it's it's interpreted in terms of triangle as the fraction of all the possible triangles in my neighborhood that exist. Okay, so for a node U, like this, I look at my neighborhood. Yeah, I count how many triangles I could have at max. If everyone was connected to everyone, how many triangles I would have. And I count how many triangles do exist. So in this case, for instance, there are 2 triangles, right? This one and this one in my neighborhood. And the possible triangle is 6. So the clustering coefficient is 1/3. Another interpretation is that it's just the density of my neighborhood. It's the density of nodes around me, not counting me. Is it good for the clustering coefficient? So the interpretation is that if it's 1, around me, everyone is connected to everyone. If it's low, then people that I know, they are not connected together. I don't know if I have more information on that. No, I think not. So yeah, one way to interpret it, for instance, is that if you have a high clustering coefficient, it can be an element to say that you're well embedded in a community. So if you're part of a strong community, you know people because these people are from the same community. So because they are in the same community, they know each other too. And so I have a high clustering around me. On the contrary, if I'm someone who is bridging different communities, I don't know, for instance, I have one friend, let's say, I'm someone who has one friend with, so for instance, in this class, and I know someone in another class, but I only know, and another person, like a professor, for instance, with classes, connect. So if you connect to different classes, you will have people from different classes don't know each other. So it means that you're kind of acting as a bridge, and so you will have a low clustering coefficient. From the clustering coefficient, which is a measure of nodes, we can define some descriptor of networks. The first one is the average clustering coefficient. So simple, you take the clustering coefficient of all the nodes, and you compute the average. So you get some value, which indicates how strongly nodes in the graph have a high clustering coefficient. And the other one is the global clustering coefficient, which is computed on the whole graph, and not by doing the sum of all nodes, but just by counting, basically comparing the number of triangles in your graph with the number of possible triangles in your graph in general. So you have to be careful if you use this one, which is often used in the literature. But the problem of this one is that you're taking the average with giving the same weight to a node with a small degree and with a big degree. Okay, so if you have a very important node, which is connected to 1,000 people, then the clustering coefficient usually will be something which is relatively small, because if you have, so let's take an example with Twitter. So if you Donald Trump, you have connection with millions of people, but these people are not connected all to each other. They are people from different backgrounds. And so if you have a very, very large node like Trump, your clustering coefficient will be close to 0. Because most of the people you're connected with, they are not connected together. On the contrary, if I take someone, I don't know, like my father who joined Twitter, he will have only me and my sister, and me and my sister we are connected. So if you compute the clustering coefficient of my father, it will be 1. 1 because all the people nodes are connected together. So the problem is that if I take the average between Donald Trump and my father, it's 0.5. But you see that, as we said, there are much more small degree nodes in networks. And it's much easier for small degree nodes to have very strong values, so either 1 or 0. So in the end, you will end up taking the average between a lot of 0 and 1, and the large degree nodes, which are actually very important in the network, they won't contribute much to the score. Yes?
Why don't you use the degrees as weights?
Yeah, that could be a possibility. If you want to do that, you can. Exactly. So it really depends on what you want to interpret. But the average clustering coefficient is often used on this way, and you have to be careful when you interpret it. So that's why it's probably better to use this definition, which is easier to interpret. Yes?
Why is there three?
Yeah. It's if I'm not, I think maybe I might have. So the problem is that it's easy to confuse between the triads and the triangles. So the problem is that each node, if you when you count the number of triangles, you often have this tree that appears because if you take a triangle, the number of triads, each node belongs to this triangle from its point of view. So if you compute the number of triangles as the sum of triads of each node, then you will have to divide by 3 at the end to get the number of triangles. So I will check if I have not made a mistake here. Yeah, because I defined my number of triangles by already dividing by 3. And I think I changed that in the middle of when doing the slides. So it's probably a mistake. I will check it. Yeah, I changed a lot of things during preparing this class this year. So in particular, I've created all these things which are in the cheat sheets that I have introduced before, that I've shown you before. So it's really possible that there are mistakes in it. So do not hesitate to tell me if you see some error, and I will check it. I will check. So an interesting property of the global clustering coefficients is that in random networks, the global clustering coefficient is equal to the density. Why? It's because if you have A and B, A connected to B and B connected to C, then the probability that the edge between A and C exists is just the probability that a random edge exists. So in random networks, this global clustering coefficient is equal to the density. And as we have seen in large graph, this clustering, the density tends to be very, very small. So we know that in large graphs, the sparse graph, few edges, the clustering coefficient will be small. Okay, so very, very small, as we have seen with 10 to the power minus 5, for instance. While if you compute the clustering coefficient of real networks, like Facebook, you get 0.6, 0.56, so you get very, very high value. And this really tells you that these graphs are not random, but have this property that if you know someone, if you know two people, they are more likely to be connected than random nodes you will take in the network. Again, it's really obvious if you think in terms of social networks. If you think about all the people you have as friends on Twitter, on Facebook, or whatever, they are much more likely to be connected than if you take two random people, which will be one in Brazil and one in in the United States, for instance, or Germany or whatever, the probability if you take two random nodes that are connected is very low. But if they are your friends, basically they have common things in common with you, so probably they have a higher chance to be connected. And there are other phenomena at play. While you can also note that some of the real networks can have a low clustering coefficient. For instance, if you take the road network or the described before, you see that the clustering coefficient is much lower than in social networks. And it makes sense because if you look at a road network, so if you have an intersection between one road and another like this, in general, they are not, again, connected just at the next intersection. Very often, for instance, in cities, you have squared. So if you have a squared pattern, you don't have a high clustering coefficient. And if you have a triangle-shaped city, you can have a high clustering coefficient, but it's not that common. Okay, let's talk about path, walk, and distance. So moving in a graph. We will define a walk as a sequence of adjacent edges of nodes. So for instance, sorry, it's on this tree. So a walk, you have, for instance, a walk on this graph can be 1, 2, 5, 1, 6. This is a walk. You are allowed to move randomly on your graph, and you can go back to the same node. A path, on the contrary, is moving without going back to the same node. So, for instance, 1, 2, 4 is a path and a walk, but 1, 2, 1 is a walk, but is not a path because you're coming back to the same node. In the network science community, sometimes people use these two terms interchangeably. So they are strict in the graph theory, but in network science, sometimes people use walk to mean path. The path length is very simply how many hops you have. So what is important here is to remember that the path length is the number of hops and not the number of nodes. So if I'm talking about walk 1, 2, 5, its length is 2. You go through 3 nodes, 1 to 5, but only 2 hops, 1, 2, and 2, 5. By convention, the path length is the number of hops, of edges. So the weighted path length is just the sum of the weight and pointer, right? So between A, B, and C, for instance, in this case, the weighted path length is 9, 4 plus 5. The shortest path is between two nodes is the path of minimal path length, and often it's not unique. So for instance, if I ask you what is the shortest path between 1 and 3, there is a single one, which is 1, 2, 3. But if I ask you what is the shortest path between 6 and 2, then there are several options. There is 6, 1, 2, and 6, 5. So there are two shortest paths. Sorry? Yes, you're right. Sorry. This example, it's 6, 2 is length 1. So it's better. But if I take another example, I don't know, on this graph, if I have one, but you understood the idea. So you can have several shortest paths. And then you have the weighted shortest path. So the weighted shortest path is the path of minimal weight. So for instance, if you have, do I have a good example on this one? I don't think so. So for instance, yes. So if I want to go from A to D, you have a shortest path in terms of hops, which is A, B, C, because it's only 2 hops, while if I do A, C, E, D, it's 3 hops. And yes, I have another possibility, which is A, B, C, D, but it's longer. And the weighted shortest path in this situation is A, C, E, D, because it's 2 plus 3 plus 4, so it's 9. While if you go to this one, even though there are only 2 hops, it's 10 plus 4, so it's 40. Okay? And we will note the distance. The distance between nodes 2 and B is the length of the shortest path. Okay, so the shortest path between 1 and 3, the distance between 1 and 3 is 2. Because the shortest path is has 2 hops. Okay? So I won't go into the details, but as you can imagine, the problem of finding the shortest path can be quite difficult when you have a large graph. So if you just want to compute the distance from one node to another, you need to do some breadth first search. So you're taking A, you're taking the neighbors, and so on and so forth until you reach F. So the problem is that if you want to know all the shortest path, which is needed for some algorithm you will see later, if you want to know all the shortest path between all the nodes, if you do that from each node, the complexity is terrible. But there are some efficient algorithms. So I won't detail it here, but if you're interested, we will also in the practicals, you can try to play with it to discover all the shortest paths in a more efficient way. So in the complexity in number of nodes cube of number of nodes. Okay, so I defined the length, the distance between nodes, and now I can define 2 properties of network. One, which is the diameter. Diameter is the maximum distance between any pair of nodes. So this tells you if in your network, if there are who are the 2 most separate nodes, and it tells you at which distance they are. And something which is more used and more characteristic of your network is the average distance. So you compute what is average distance between all your nodes, the shortest path, and this tells you something about your network. And what does it tell you? Well, to that we can talk about the Milgram experiment. So it was not explained in another class. No. Okay, so I can explain it here. So the 6 degrees of separation, well, it's a term which is actually quite used in English, which is known by many English speakers. 6 degrees of separation, and it comes from an experiment made by a sociologist called Milgram. In the 60s. So in the 60s, the idea was to see if the society was a small world. So a small world, this idea was, do you know someone who knows someone who knows someone who knows someone, basically, and who know anyone on the in the social network. So it's to count what is the distance between 2 people taken at random. So the idea is really to take the population of the US and to take 2 people at random and to check if an information, so a mail, a physical mail, can be sent. You give it to the first person and you tell this person to send it to the destination. But if this person doesn't know who the destination is, he just knows the name and a few information. Like, for example, what is his job, John, and this kind of information. So the name and maybe location also. Yeah, location also. And so the idea was to check how many. So it's like, you know, this list that someone you received maybe when you were younger, where someone sends you a postcard and tells you have to send to people, and they will send after 6 hops. They will after 6 times they will send you back a postcard. So here the idea is relatively the same. You have to send your mail to someone you know, and you have to write your name on it. So you write your name, you send to someone you know that you think you think that this person might know the person that is the destination. So in the experiment, so the first person here was not taken at random. So Milgram chose one person, I think, in New York, and set this person as the destination. And then he picked randomly people in the world of the US, and give the rules, which was to try to send a mail to this person. And so this way he could record how many hops, because every time someone receives the mail, he wrote his name and then sent to someone he knew, and so on and so forth, sending to the most relevant comment. And the conclusion of this was that in average, the mails arrived after 6 hops. So it means that you know someone who knows someone, 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 who knows anyone in the US. Well, that's the general idea. And so this was kind of an amazing result when it was published, but it encountered a lot of criticism. So of course, one of the problems was that many mails did not arrive and they were not counted. So he made the average of the number of hops between all the mails that arrived. So the criticism was maybe the one that did not arrive, they would have taken much longer. So this is a bias. Of course, it was a small sample. And another criticism in the other direction was that people could not choose maybe the faster or the shortest path. They took a path which seemed good for them, but maybe it was not the shortest path. Maybe they could have done it in a smaller number of hops. So actually, even when I started my PhD, this was still something which was debated. I remember a conference in which someone was just saying that this was not a real thing because if you were taking a really large network, the distance would be much longer. But actually, then people started to collect real graphs. It became easy because of things like MSN Messenger or Facebook or even the World Wide Web. And people collected the whole network and computed the shortest paths using algorithm. And what they obtained in a paper on Facebook is this. And if you look at the average degree of separation, you see that in this case, it's actually less than 4. So it's even shorter than what was computed by Milgram. So in Facebook, you know someone who knows someone who knows someone who knows Donald Trump, Barack Obama, and so on and so forth. So everyone. And I think that they added that the diameter, so the longest path possible in Facebook was something like 18. So there are some long paths, but they are very, very rare. There any question on the shortest path? Yes? Yeah, so this is still, I think, a debate. So we don't know if you are taking everyone. So the problem is also that on Facebook, you don't have everyone. And you have spammers who create links to maybe many people. So there are still, of course, many biases in this computation. So I hope one day we will all have a chip to have record our contacts. You know that maybe the government will do it to track COVID. But if you haven't installed the software, then it's not working. But if everyone here installs the software, then we can get the data and we can answer the questions. Hopefully for network scientists and not hopefully for others. Of course, it also depends a lot on your definition of friendship, right? So if you take the shortest path in terms of friendship, in terms of close friendship, in terms of acquaintance, in terms of knowing the name, it will probably have different results. And we will see also in later classes that one factor which is difficult to take into account is the importance of hubs. So if you have some people, so for instance, if you consider that you know Donald Trump because you know its name, his birth date, and so on, then obviously the shortest path between everyone is very, very short. It's basically 2 because everyone knows Donald Trump. But if you, so the hubs change a lot this property. So now that we have defined measurement of networks, we can define an important property, which is a small world network. And for this network to be small world, according to the literature, it needs to have at least 2 properties. The first property is to have a short average distance. So short is not really precise, but basically it should be around or lower than the log of the number of nodes. So really small compared to the number of nodes. So everyone can be able to reach everyone in a short number of paths. And the other property is that it needs to have a high clustering coefficient. So a large number of triangles, right? And why this property considered important? It's because this property is not verified in simple random networks. So if you generate a network by just adding edges randomly in nodes, or even if you take some basic graphs like a grid or some regular pattern, usually if the density is low, so if you don't have too many, if the network is sparse, if you don't have a lot of edges, then you won't have these 2 properties. While on the contrary, if you take real networks, social networks, but also a lot of other real networks, nearly all of them have this small world property. So they verify these 2 properties. So that's why it's considered important, because it's a major difference between theoretical objects with which, for instance, graph theory has worked a lot. With graph theory, you consider that you have a random network, and then you try to define it and to find properties on it. But if you take a real network, it has very different properties. It has this high clustering coefficient. While so in a random network, if you generate a random network, even if it's sparse, you will have this property. You will have the average distance, but you won't have the high clustering coefficient. And if you generate some regular pattern, you can easily add some high clustering coefficient, but not easily the low average distance. So that's why a small world is something a notion you will encounter a lot in network science. A network needs to be small world for some properties to exist. Another notion is the organization in core and periphery. So this is more a global organization of the network. Very often we consider that a network has a core, which is a set of nodes which are strongly connected together. And then if you go to the external areas of the network, you will find some nodes which are loosely connected together and loosely connected to the core. So often a network is organized in this way, and you can define this by computing some K cores. So the K core consists in one core is defined. After that, okay. A K core is defined as being the largest graph, such as all the nodes have a degree at least K. So for instance, if the graph is completely connected like this, all the nodes belong to the one core and to the one shell. I will explain it. But the one core means that all the nodes have at least a degree of 1. Okay, if there was a single node along here, it would not be part of the group. But then, if I need to compute the two core is the set of is the largest subset, such as all the nodes have a degree of 2, but it's not as simple as taking all the nodes with a degree of 2, right? Because this one, it has a degree of 2, but it's not part of the 2 core. Because so this one I know it has a degree of 1, so it's not part of the 2 core. This one even. But now, this node, when I remove these two, this node it has a degree of only 1. So it's not part of the 2 core. So I need to recursively, like this, remove the nodes with a degree below k until I reach a state where all the nodes which are inside and have a degree of 2 in the subgraph of the 2 core. Okay? It's clear? So in the 3 core, all the nodes have a degree of 3, a degree of 3 in the 3 core. Okay, and so the 3 core, the 2 core is composed of all the nodes in the 2 core, and so that have a degree of 2 or more. And the 2 shell is composed, so the shell is only this one. So it's the one that belongs to the 2 core, but not to the 3 core. So this, with this property, you can define the if your network has a strong core periphery structure by looking how many nodes you remove every time that you move in a higher with a higher k. Okay, so another notion is the notion of triad. So triad is just counting the number of, so in this case of directed shapes. So for instance, counting the number of times you have this shape is, and counting the number of times you have this shape, it tells you a little bit about the structure of the network, because in this case, you see that it's, for instance, if you have many times this pattern, so if you don't see it well, it means you have an arrow from this node to this one and to this one. And this might be characteristic of a network in which you have diffusion. So you have people who are diffusing to other people. They are sending messages to several other people. While this one might be the contrary. It's when you have, it's not diffusion. It's, for instance, in popularity, in Twitter, you have this kind of patterns. You have someone famous, and you have many people following this person. Right? So in Twitter, you have this type of triangles, but not this type. And in other type of networks, you might have the opposite. And so the idea of using these triangles is to compare the number of each of the small triangles you have to the number of triangles you would have if the network was random. And so you compare this between two networks or between a network and a network. And it tells you what is the, and it tells you, so it can tell you something about your network also. Graphlets are just frequent type of subgraphs. So I won't say much about it, but if you encounter the term graphlet, for instance, maybe in your network, this subgraph is very common. You encounter many times. So it can be a way to, for instance, encode efficiently graphs or something like this. I will maybe not do the matrix part of this class. So you can read it if you want, or maybe I will introduce it when needed. I just give some basic elements about, so the basic matrices, I think some of you have seen it in other classes, the adjacency matrix, the Laplacian matrix, and random walk matrix, and some properties of them. And I wanted to just finish the class by giving some examples of a graph analysis done on Facebook. So just to give you some ideas of what you can do with this notion we introduced. So first, describing the size. So we will talk about a network collected at Facebook with 721 million users that were active in the last 20 days. So active users. It has 68 billion edges. It has an average degree of 190, right? 190 average number of friends. It has a median degree of 99. So you observe that the median and the average are quite different. This is due to some imbalance I talked about before. And the largest collected component is 99.91. So what this is saying is that everyone is connected to anyone by a path. So there are some people who are not connected. So I don't think they elaborate on this on the article, but I suppose they are just people who join and never added any friendship. So they are alone in the graph. We can compute and plot the distribution area. So I think so the information is here. So you have for each component, you have the size. So the size, this is the largest connected component. And this is the other one. And so you see that they are not all singleton. Some of them are singleton. They have no connections. But there is a connected component with, so it's not 10,000, so it's about 1,000 probably. 1,000 nodes. So I don't know who they are, but they are connected only to themselves and not to the rest of Facebook. So maybe some secret society or people in a remote island. I don't know. We need to investigate. But this can be interesting to see what's happening. So for instance, probably that you need to remove all the nodes there to have something more. Probably there are some erroneous or strange nodes. I can plot the distribution of degrees, and so I can plot the distribution of degree, for instance, in the US and in the whole network. And I see that happening at the end. Do you have an idea why? What's happening here? So before I said that in social network, usually you have some people who have a very large degree. And here, apparently, it does not really, the maximum degree seems to be 5,000. So it's just because at that time, there was a limit on the number of friends in Facebook of 5,000. So by definition, you cannot have very large hubs. Okay. So you can study one property compared to another. So if I take the degree of node and I compute the average clustering coefficient of those nodes. So I take all the nodes with a degree of 20, and for all of them I compute the clustering coefficient and I compute the average. And what you can observe here is that it tends to decrease, as a little bit like I was explaining in my example for the clustering coefficient. When you have a degree of, when you have 1,000 friends, usually many of them are not connected. But if you have only 5 friends, well, they tend to be more often connected between themselves. So more interesting, the first one here is plotting the degree, the average degree according to the degree. So if I have a degree of 200, what is the average degree of my friends? And what is interesting is that I observe that if I have a degree of 200, I have 200 friends on Facebook, in average, my friends, they have 400 friends. So this is known as the friendship paradox in networks. And it has been proposed that it's an explanation of why it's sometimes depressing to use social network like Facebook or whatever. It's because if you compare with your friends, they are more popular than you. So do you see why? Where does this comes from? So it actually just comes from the definition of the degree. It's a degree is that you have a high degree if you have many friends. So by definition, very popular people are connected to many other people. So in average, if you take someone at random, it will be connected to very popular people because these very popular people, they have many friends, right? While those with a very low degree, they are connected to few people by definition. So it means that very few people are connected to low degree. Okay, so if you plot this, you observe that it's the opposite relation when you get to high degree nodes. So if you look at people with 1,000 friends, then in average, their friends, they have only 800 friends. So if you're very popular, of course, you're connected to people who are less popular than you. But in average, you're connected to people who have an average number of friends which is higher than you. Okay? More precisely, you can look at the degree of your, what is the degree of your friends according to your own degree. So for instance, if I have a degree of 50, so I have 50 friends, then, if you have a degree of 50, if you have 50 friends, then you see that there is a relation that actually the majority of your friends, or many of your friends, will have a degree also of 50. If you have a degree of 100, so the yellow curve, you see that the most common degree of your friends is also 100. So this means that you're connected to people who have a number of friends which is similar to you. So it means it seems contradictory with this one, but it's not, because here you have a log relationship. So actually, it's not a bell curve, but it's you have actually the values here are much bigger. So if you take the average, it will be the average will be of people with a degree of 50 will not be 50, but it will be around here. So it will be above 50. But if you look at most of your friends, they will have a degree similar to you. You can do the same thing with properties of node, and this is something we will see in more details in the next class, like age, for instance. So this is probably something you know intuitively, but if you have an age of 30, then most of your friends have an age of 30. And it's very clear in the data. Yeah, so if you have an age of 50, you see that it's 50. There is maybe one exception, which is 60. So if you are 60 years old, you have some friends of 60, but you have also many friends that have around 30 or 40 years old. Well, you can guess what's happening. It's probably grandparents being friends with their child and grandchild. But otherwise, you see this very clear pattern. And finally, you can also study some high level of connection between parts of the network. So here, for instance, is the number of edges between countries. So on the x-axis and on the y-axis, you have countries' IDs. So you cannot maybe read it very well, but here you have France, Belgium, Portugal, probably. So we are kind of ordered actually according to the values. And so you have countries, and the the color of each cell represents the strength of the connection of the number of friends between people from one country to another country. So the first thing you observe, relatively obvious, is that the strongest values are on the diagonal. So this tells you that you have many friendships inside the same country. But if you look at a more general picture, country by country, you see that there are some patterns that emerge, which is something we will see in a later class called, we call it communities. And these patterns tend to have some logic behind it. So I don't remember exactly how it's, what are the countries here, but here you have Taiwan, Hong Kong, Singapore, probably Malaysia, and Philippines, and so on. So here you have maybe East Asia. Here you have, can you guess? Probably, yeah, Colombia, Ecuador, Venezuela. So you have some groups that will correspond to South America. Where is the US? Do you have it? Yeah. Yes. So you can see that it's strongly connected to maybe more to this part, right? And here you will have, I think, Europe probably. And what is interesting sometimes is to look at what are the kind of the exceptions. So so this one is Canada probably, which is strongly connected to some country here, but we see that it's rather part of this group, but also it has a strong connection with something, Great Britain, maybe, New Zealand, probably, and so on and so forth. So you see that you have this kind of structure, this emerge, and from this you can infer some organization of the global network in terms probably of languages, because people tend to have more connection with people who speak the same language as them, obviously, but also you have some geographical proximities, and so on and so forth, and so on and so forth. And I think I will stop here. So as you have seen, 2 hours is quite long, especially when giving definitions. That's why from Thursday, you have only 1 hour of lectures, and after that, we experiment with what we have learned on real networks. And that's all for today. Thank you.
Thank you.